Well, my name's Jacob. It's
Hello,
very
my name is
easy.
Kevin.
My name's Chris.
And we're going to be doing our presentation over linear regression and lines of best fit for wins of selected professional sports teams. So if our goals and motivations for this presentation, on our goals, I think the most important one that we really wanted to get to was figuring out what higher degree lines of best fit look like on erratic data. Um, Most of our data isn't going to be very nicely approximated using, a cubic or quadratic line of best fit. And so it'll be interesting to see um, how higher degree lines of best fit can map the data. Um, we thought it might also be interesting to see if there was a sport that was best suited to these methods. Maybe the error for one sport is different than the other. And also, um, sports are a universal and excellent application of math and statistics. So it'd be interesting to see another application of math and statistics to sports as well. A few of our hypotheses. We think that as you increase the degree of the line, that we will start to produce more accurate results or results with less error. And we also think that the error will be similar for each team and league. A note about our data. So the data that we're dealing with is how many wins each team had per year. So for example, in the year 2018, the Bears won 12 games. And year, we really mean season. We chose for our data to start at 1960 and go until 2022. The reason that we chose 1960 is because, well, some leagues are older than others. The NFL and the NBA are really relatively new leagues compared to the MLB and the NHL. And so we want a nice start point of comparison. And also per team, some teams are younger than others. For example, the Boston Bruins have existed continuously in Boston since 1924, but the LA Lakers haven't existed in LA until 1960. And here we can see some of the websites where we got our data from. So what sort of numerical analysis methods are we going to be using? Well, polynomials of best fit, most notably the linear line of best fit, the quadratic line of best fit, and the 80th degree line of best fit. Really, the whole point of this numerical analysis method is to minimize the sums of the squares of the differences in order to produce a line that will fit most of the amount of data with the least amount of error. So sometimes this works well, but other times it's perhaps not the best interpolation method. For our implementation, we mostly just use Python programming, using libraries such as sklearn, NumPy, and matplotlib. So the first thing that we'll look at is our linear regression, or our linear line of best fit. As we'll see, the error for these is very high, but they will tell us another interesting aspect of these teams, and that is correlation between years and wins. So the first team we'll look at is our baseball team, the Chicago Cubs. Since 1960, they have only won about 48% of all of their games played. They have one World Series championship win since 1960 and 2016. The number of seasons below 50% wins is 38, which means that 61% of all seasons since 1960 they have lost more than they have won. And so what does the linear regression tell us? Well, it says that for every 1 year increase, they'll win 0.08 more games, meaning that the Chicago Cubs have a very weak, almost non-existent, positive correlation between time and winning. The Boston Bruins, our National Hockey League team, their win-loss ratio since 1960 says that they've won nearly 60% of all of their games since all of their games played since 1960. They have 3 Stanley Cup champion wins since 1960 and 1970, 1972, and 2011. Number of seasons below 50% win is only 24. So that means that only 38.7% of all seasons since 1960 did they lose more than they won. And what does the linear regression tell us? It says that for every 1 year increase, they're projected to win 0.23 more games. So this is a little bit more significant than the Chicago Cubs. The Boston Bruins have a moderately weak positive correlation between time and winning. Here's our football team, the Chicago Bears. Their win-loss ratio since 1960 says that they've only won 48.7% of all their games played. They actually do have one Super Bowl win since 1960 in 1986. Number of seasons below 50% win is 33, meaning that 53.2% of all seasons since 1960 they've lost more than they've won. And the linear regression tells us that for every 1 year increase, we expect them to win 0.01 more games. So the Chicago Bears have a very weak, almost non-existent positive correlation between time and winning. And lastly, for the linear regression is our basketball team, the Los Angeles Lakers. Their win-loss ratio since 1960 says that they've won nearly 60% of all their games played since then. They have 12 championship wins since 1960. The number of seasons that they have below 50% win is only 15, meaning that only 24.2% of all seasons played since 1960 have they lost more than they've won. But what does the linear regression tell us? It says that for every one increase in year, they win negative 0.13 more games. So the Los Angeles Lakers have a moderately weak negative correlation between time and winning. It's interesting that one of the winningest basketball teams of all time has a negative correlation between time and winning. But really the culprit for this is some pretty bad outlier seasons in recent history, as you can see there between the 2010 and 2020 mark. And those are bringing it down overall. So in recent years, they've done worse than they have been great in prior years. Here we can see all of them plotted next to each other. Most notably, we'll see that these lines are a terrible approximation of the actual data. There's very high error, so high that we don't compute it. But crucially, what this does tell us is a general trend between time and winnings but for each one of these teams.
Next, we'll examine the quadratic line of best fit, which should give us a slightly better insight into the trends of the data and over the rigidity of the linear line of best fit. So once again, starting off with the Chicago Cubs, here is a fourth degree polynomial line of best fit on the data. And with this curve, we are allowed, again, a little bit more insight into the data trends over time. We see at the beginning of our chosen time frame between 1960 and 1980, we have a positive trend as they were doing pretty well during this time. And then we have a dip pretty much from 1980 up until recent years, as during that time they were doing pretty poorly, as is as it goes with the Cubs, as is typical. But then we have a spike in around like 2010 to 2020 when they won the World Series and started doing better again. So again, key takeaway from this plot is just a bit more, not a complete view of the data, but a bit more insight into trends over time. Moving on to the Boston Bruins, we again see their spike in wins per season between 1960 and 1980 mapped pretty well, with a pretty steep increase of the curve and a peak during that time. Then we experience a trough between 1980 and 2010, when their wins started to decline, and again another peak when their wins started to increase again after that time. We see this curve maps the flow of the points fairly well, and we'll explore the accuracy of this during our error analysis later in this presentation. Chicago Bears, we see again what we'd expect. The Bears are notoriously a pretty bad team, so we see a trough right away. at the beginning, during the 80s and 90s, we see a spike when they were doing well, when they won their Super Bowl in the mid 80s. But again, that did not last forever, and we do see another trough going into present day with the Chicago Bears. Yes, as they are not the greatest team in the NFL. Lastly, we have the Los Angeles Lakers, which is fairly interesting, as Jacob alluded to during the linear analysis. The Lakers are a very good team. They have a very high win ratio, but we have one large peak, which is what we'd expect for a team with this many wins per season over time. However, a bit of a drop off in recent years, as we expect, because we do have those outlier seasons that are not necessarily representative of the Lakers' typical performance, but it is mapped nonetheless on our fourth degree polynomial curve. And similarly, we have all the plots next to each other. We can see the data for all four teams, as well as the scatter plots that we use to generate these curves.
All right, now I'm going to talk about our 80th degree line of best fit. With these polynomials, you can see a lot of these smaller trends in between the spans of like 2 to 3 years. You can see smaller trends. You'll notice at the bottom, we went from 0 to 60 years since 1960 rather than the actual years to allow the computer to calculate these numbers without overflowing. And with these, with this 80th degree polynomial, you'll see that this trend generally follows the same trend as our fourth degree polynomial, with a lot more variation along the way, so that it's getting as close to as many of the points as possible, trying to lower that error. You'll see that a lot of the outliers are also included. So you can see that the Chicago Cubs, when they were going to the World Series, that point is now in this polynomial line. Now we'll move on to the Boston Bruins. You'll see that this trend also very well follows the fourth degree, where it starts off low, goes high, drops a little bit, and then starts going upwards again. And then again, a lot of the outliers are also in this polynomial. Here we have the Chicago Bears. Again, it's following the trend. This one was starting off low, then going high, and then going low again. And then, as usual, all these outliers are getting kept within the polynomial. And then here's all four of them together. And then we're going to see later how all of these three different polynomials will fit together.
So we'll get into the results here. We can see each plot next to each other. As Chris alluded to, they see how they fit together and map the data with varying degrees of accuracy. Just a comprehensive view of our findings. And then discussing the error, we computed the mean square error for each curve. For the quadratic polynomial line of best fit, the Cubs had a error rate of approximately 13 wins per season, meaning that it was off by about 13 wins per season. The Bears quadratic curve was off by approximately 3 wins per season. The Bruins 8 wins per season, and the Lakers 11 wins per season, giving us an average error for the quadratic polynomial line of about 9 wins off per season.
Yep. And then for our 80th degree polynomial, we saw a reduction in that error. For the Cubs, you'll see that instead of 13, we got 9 wins off. For the Bears, instead of 3, we got 2 wins. For the Bruins, instead of 8 wins off, it was 5 wins off. For the Lakers, instead of 11 wins off, it was about 6 wins off. And then overall, we went from about 9 wins off for the accuracy down to 6 wins off for the accuracy.
Right. And then looking at the deltas between the errors of the quadratic and 80th degree polynomials, we see negative delta or negative change between the error rates, meaning that for each team, the 80th degree polynomial improved our lines of best fit and was a more accurate method, as we hypothesized. Here is a visual about the errors of the quadratic and 80th degree polynomials. put next to each other, again, we observe a improvement in all cases for the 80th degree polynomial.
Yeah, and here it is a reasonably good question to ask. Are these lines good at extrapolating data? And the results are no. These lines are terrible at extrapolating data. As we can see, interestingly, for doing this, the MLB season is over while the others have continued, so we can actually compare to see in 2023 or 2024 season how well they've done. So for the Cubs, the linear line expected wins were 74, while the quadratic line expected wins were negative 1,176,615, which is not possible. So, and the actual wins for the Cubs in this past season was 83. So, not great. For the Boston Bruins, the linear expected wins was 44, and the quadratic expected wins were some large negative number. We have yet to see if this will actually be a reasonable metric for this upcoming season, but it looks like they're most likely going to win more than 44 games. For the Chicago Bears, the linear expected wins was 1, and the quadratic expected wins were about 265,000. And so far in this current season, they have 4. So the linear has underestimated it, and the quadratic has perhaps overestimated it. And lastly, for the Lakers, our linear expected wins was 53. Our quadratic expected wins was negative 43,000, which isn't possible. And so far, they actually have 13 wins. So it may be safe to say that they will probably get above 53 wins this season. So in conclusion, most of these lines are not very good at extrapolating the data. And in order to accurately predict whether or not a team is going to be successful in the future, you would need much, 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 much more data and information about the team and about everything else in order to more accurately predict it. So now we can talk about the conclusions that we came to and the future of our work. So what things did we conclude? Well, we did find that if we increase the degree of our polynomial, that the error does decrease. So the linear had the highest error, quadratic had less error than the linear, and the 80th degree had less error than the quadratic. So as we increase that polynomial degree, we start to get less error. The error was very different for each team and league. Obviously, there's a lot of variables that go into this. Most likely, one of the bigger culprits is the number of games played per league, and many other different factors that can affect that. The extrapolation was very inaccurate. As I said, wins in a season are not enough information to determine the future of a team. What remains left to do is we could see the interpolating power of these polynomials. So we could take out some of the data and see how well it interpolates it. And perhaps we could do a more thorough extrapolation to see if, we took some trained data, so to speak, and then compared it to actual other data. But this is a little bit more difficult and not as useful in the sports world, considering that things change rapidly every year. And perhaps for the future of our work, it would be interesting to see if we could do this for every single team in each one of the 4 leagues and see if there actually is a team or league that is best suited to these methods that has the lowest error, and that might be interesting to explore.
Thank you very much for your attention.